Okay, here's section 5.7, de Moivre's theorem. Okay, and this gives us the idea of the roots of unity. So this is theorem 5.7.1, and it says if n is greater than 0 and n is an element of the integers, so it's a positive integer, then cosine theta plus I sine theta to the n is cosine of n theta plus I sine n theta. Okay, and that just came from our properties of exponentials. Right, if I have e to the z to the n, that is equal to e n z. Well, okay, for my z, I'm going to use I theta. So e to the I theta to the n is equal to e to the I n theta. And so this side is the left side here, and that is the right side there. So just using exponentials makes that a very simple proof, using those properties of exponentials. Okay, so now from that, we then look at theorem 5.7.2, and this is the roots of unity is what's going on here. And here they say the equation z to the n equals 1 has n distinct solutions. And those solutions are specifically, now they use I guess that's a C. I can't make them very well, but I'll try to do what they have there. So the answer is e to the 2k pi I over n, and k equals 0, 1 up to n minus 1. Okay, so these are, the geometry of this is they are equally spaced on a circle of radius 1. So this is z equals 1. And, so they may be here, there, depending on what n is, maybe there. If I got them, I'm kind of close. There we go. So they'll be equally spaced around. So that's a pretty neat sort of thing, and they give a nice picture of it. And so the proof, I guess, is, let's just demonstrate that we get it right. So if we look at the nth root, or no, sorry, if we look at the kth root to the n, I was looking at that upside down, we have, e to the 2k pi I over n, raise that to the n, and, well, that'll be n over n, so that's just e to the 2k pi I, and we know that that's 1. We've already had that by de Moivre's theorem. Okay, and so then we also know the magnitude here is 1, and so if all of these have magnitude 1, they have to be on that circle, and since it's 2 pi around, then I know that when I go 2k pi over n, that for 0 to n, well, actually n minus 1, then these are going to be equally spaced. Okay, so, there you go, roots of unity. Now, then they say, well, what do you do for a more general equation? Okay, so suppose you have, so more generally, suppose I want to solve z to the n equals a. Now why they use an a all of a sudden, not sure, but a is an element of the complex numbers, and a is not equal to 0. Okay, then what we can do is if we let alpha equal arg z, so that a equals the absolute value of a, so there's that, and then e to the I alpha. Okay, so I think actually they mean, so I'm just kind of reading their proof, but I think they have a typo there. See, they say let alpha be arg z, but then they say a is this. And, that would be how I would write a, not z. So see, I think they don't have that correct in their proof. I believe that should be arg a. And so if we do that, then we can state this. Okay, and now they say, well, if w equals a, the absolute value of a to the 1 over n, and e to the I alpha over n, we have w to the n would be all this to the n, but I just multiply exponents, so I'll cut to the chase and say, well, that would be absolute value of a, e to the I alpha equal a. Okay, so they're saying that, that is a particular solution. Okay, so they say, so w is a particular solution. And and then they say substituting for a in the original equation. Okay, so substitute Wn equals a. Okay, so we found a solution, so that's what they're trying to get at. We found a solution, but it seems like there probably ought to be many more solutions. So we found a solution, and then so we substitute that, and we have z to the n equals w to the n. But now if I divide both, I have both sides by w to the n. I have z over w to the n equals 1. And so then I can get the solution for z over w, right? So z over w is equal to, well, let's see, what the heck was that? Right, e to the 2k pi I over n. So this is e to the 2k pi I over n, and that was for 0, 1, up to n minus 1. So that's z over w. And so if that's z over w, I can just multiply z and get w times e to the 2k pi I over n, like that, 0, 1, up to n minus 1. And then the w I can rewrite in terms of a, right? So this is absolute value a, e to the I alpha. This is a to the 1 over n, actually. And this is e to the I alpha over n. Is that right? W to the n is that. Yeah, I alpha over n. And then times e to the 2k pi I over n. Again, k equals 0 up to n minus 1. And then, so that's good, or I could keep going and put the exponents together. So I have absolute value of a to the 1 over n, and then e to the I alpha plus 2k pi all over n, like that. And again, k can go from 0 up to n minus 1. Okay, so from those two things, we have example 5.7.1. If I want to do z to the 5th minus 1, and I'd like to factor that, so they say factor this thing. Well, so I need the roots, so I want to solve z to the 5 equals 1, and what I get for that is e to the 2k pi I over 5, k equals 0, 1, 2, 3, and 4. Okay, so those are my roots, and so I could write z to the 5 minus 1 as z minus 1, okay, that's k equals 0, then times z minus e to the 2 pi I over 5. And then z minus e to the 4 pi I over 5 times, got a couple more here, z e to the minus 6 pi I over 5, and times z minus e to the 8 pi I over 5. Okay, there I factored that. And then if I, now these are not principal args, okay, in the textbook, then they mention the principal arguments. Okay, so I could also write this as z minus 1. Now, z e to the 2 pi I over 5, that's fine, because 2/5 pi is between minus pi and pi. And 4/5 pi is as well, e to the 4 pi I over 5. But 6 pi I is not. That's bigger than pi, so that gets me into the negative regions. And so that's, let's see, 6 pi I. Let's see, 6 pi I. What the heck is that? Well, so, a 6 pi I over 5, that is. So as I look at this, right, I gotta think about what these are, and I came over this way, 6 pi over 5. Okay, so I am here, this amount is pi over 5. So if I come back this way, that's z e minus e to the negative 4 pi I over 5. And similarly, when I do 8 pi, that gets me way over here, so this gets me to the 8 pi over 5, which leaves 2 pi over 5 in there, and so that's z minus e to the negative 2 pi I over 5. So if I want to use principal arguments, I would write it factored this way. Okay, that's example 5.71, and then they have 5.72. So this is example 5.72, and here they want us to solve z cubed equals I. Okay, well, so we need to write I as some value. Now, they, oh, okay, yeah, I thought they were doing something funny, but no, they just sort of jump to it. So we want to solve this. So if I look at I, right, the magnitude of I, or the modulus of I, is 1, and arg of I is equal to pi over 2. And so that's the alpha we want. Okay, and so what we have for, in this case, our A is 1 to the 1/3, and e to the I pi over 2, and then divided by 3. Okay, so that's equal to 1 e to the pi over 6. Okay, so we had that. That was our A. That we wanted to work with, and let's see, I have to look back here at our stuff. I don't have this memorized. So, right, we had, okay, so that's our, or not our A, I guess, our W, called it A, sorry about that. We need our W here, and then times the 2k pi over 3 times I. Okay, so sorry, that should have been W. And so we have that, and so that means our Z is our W times e to the 2k pi I divided by 3 for k equals 0, 1, and 2. Okay, so we have that, and so that is just a 1, so that's nice. And so that's WE to the pi over 6 plus 2k pi I over 3 for k equals 0, 1, and 2. So now, I can just put in the 0, 1, and 2 if I wish. Now, and then we can also talk about principal arguments. So what we have is our Z0 is e to the pi over 6, which would be cosine pi over 6 plus I sine pi over 6. If I wanted to write it that way, Z1 is equal to e to the pi over 6 plus 2 pi over 3. So that's 2/3 plus 1/6, that's 4/6 plus 1/6, that's 5/6. So we get 5 pi over 6I. Oops, I forgot my I up there. And so again, I could write this as cosine of 5 pi over 6 plus I sine 5 pi over 6 if I wish to. And I could even convert those to some sort of fraction or decimal number, since we can actually do those. But and then Z2 is, well, let's see, I've got 4 pi over 3, so that's 8 pi over 6. So I get 9 pi over 6. So e to the 9 pi over 6I. Now, again, that's a perfectly fine complex number. However, that's not a principal argument. So if I want the principal argument, I need to be between pi and minus pi. So this is actually 3 pi over 2, right? So this is e to the 3 pi over 2I. So that looks to be actually a principal argument of minus pi over 2. So this is the same thing as e to the minus pi over 2I. And again, I could write that, so if I, and I could have done this with the 9 pi over 6 or whatever, but I have cosine of minus pi over 2 plus I sine minus pi over 2. Okay, and now this last one, I know cosine of minus pi over 2 is 0 and sine of minus pi over 2 is negative 1. So I can very quickly see that that's minus I. The others I'd have to think a little bit about as to what they are in terms other than cosines. But they're, we just plug things into formulas, and if we want principal arguments, we have to kind of think through those. But again, it's really no different than working with polar coordinates. And so, that's the idea. De Moivre's theorem is nice, getting these roots of unity and so forth. And we will stop this video here.